Hey everyone, welcome to Physics Pandemic Education Lesson 3. Today I'm really excited. We're actually going to start learning some new content. This is going to be Unit 5, Electricity and Magnetism. We're going to take it nice and slow. It's going to be a lot of fun. Before we get started, I would love to recommend that you have with you a calculator or your phone, your notebook, something to write with, and I would also love it if you could get a separate sheet of paper, ideally something in color, so you can start creating a formula sheet for yourself throughout this unit. Let's get into it. All right, here we go. So this is Unit 5, Electricity and Magnetism. Our statement of inquiry for the unit is that the many components of a system and their arrangement in context of the whole can dramatically change the operation of the system. I want you to take a minute, and in your notebook, I want you to think about the statement of inquiry. Think about what you know about electricity and magnetism, and I want you to give me 1 to 2 thoughts about how these two things relate. Take a second, pause the video, and when you're ready, you can resume. So, our objective. By the end of the day today, scholars are going to be able to calculate the electric force between 2 point charges using Coulombs law. This matters in life. The whole point of physics is learning about how the world around you works, right? We're actually taking everything that we see in real life and learning about the math that makes it happen. As for our class, our goal for this class is to reach 80% mastery at all times. Understanding today's lesson is going to help us be successful in the unit as a whole and be successful as we wrap up the end of the year. In case you're wondering about our TEKS, 5C, where we will describe and calculate how the magnitude of the electrical force between two objects depends on their charges and the distance between them. Our topic for today is Intro to Electricity and Electrostatic Force. So if you have not yet, please make sure you title your notes, Unit 5, Lesson 1, Intro to Electricity and Electrostatic Force. So, in order to understand electricity and electrostatic force, we need to talk about atoms. Atoms are made up of protons, neutrons, and electrons. Hopefully you remember from chemistry that protons are positive, neutrons are neutral, and electrons are negative. These 3 pieces together are usually balanced, which makes an overall atom neutral. And as I hope you recall, atoms make up literally everything. So, the charge on an electron. In physics, we use E with a little negative sign up next to it. We measure it in the unit coulombs. Now, 1 electron is equal to 1.6 times 10 to the negative 19 coulombs. Really small, right? We're talking about 10 to the negative 19. So that means you take your decimal point and you move it 19 times to the left. For reference, a lightning strike has about 20 to 30 full coulombs of charge. That's a whole lot of electrons. So, I said these charges are usually balanced, but what happens if they become unbalanced, aka we have an excess or a shortage of electrons? Pause the video, jot down what you think might happen. All right, so here are some of the things that might happen. As you can see, we've got hair sticking up due to static. Over here with this dog, again, same thing. The hair is all standing up because of that difference in charge. Pretty crazy. So, static electricity is caused by a tiny charge imbalance that results in either a net positive or a negative charge on an object. So, looking at our pictures over here, in picture number 1, you can see that both the balloon and the wool have a balance of positive and negative charges. The balloon has 1, 2, 3 positive and 1, 2, 3 negative. That means that its overall charge is 0. Same thing with the wool. The wool has 4 positive, 4 negative, overall 0 charge. As the balloon begins to rub up and down against the wool, we see that the charges start moving around a little bit, okay? And so, with the balloon, we end up with 3 positive charges, but 6 negative charges. The wool also has 1, 2, 3, 4 positive charges, and then it's left with 1 negative. So some of those negative charges move from the wool over to the balloon. In picture 3, we have the same balloon that we just rubbed against the wool, and we are comparing it with a wall, okay? The wall has a nice even distribution of positive and negative charges, But because there's such an imbalance of negative charges on the balloon would actually stick to the wall because of those positive and negative charges on the corresponding wall and wool. So in static electricity, opposite charges attract and like charges repel. Have you ever heard that? Opposites attract? Physics is why. So if we look back at this, we've got these negative charges at the edge of the balloon that are attracted to the positive charges in the wall. And that's what makes it stick. In your notes, please make sure you write down that in electricity, opposites attract, like charges repel. Now let's talk a little bit about insulators and conductors. So a conductor, we're going to talk about that first. In a conductor, our charges are able to move about freely, and our charges are really spread out. Okay, some examples include metal, water, and the human body. An insulator, on the other hand, sometimes called a non-conductor, the charges are stuck where you put them. Charges don't move around so readily. Some examples include wood, rubber, and glass. So, have you ever heard, you're not supposed to take a bath with, like your hair dryer nearby? It's because water conducts electricity really, really well. So if that hair dryer were to fall into the bathtub, what's going to happen? Charges are going to start moving around really readily, and you are going to get hurt in the process. Any of my kids that have done like home construction work, if you're working with electricity, you're supposed to be wearing, ideally you've got rubber gloves on, but if not, at least rubber soled shoes so that, God forbid, something happens, right? You're not getting an electric shock. So looking from the left to the right, increasing conducting ability, we've got rubber, then glass, wool, wood, dry air. Those are called insulators. And again, that means that our charges do not move around readily. Some semiconductors include silicon. So that means they can kind of move, but not as well as an actual conductor such as water, carbon, iron, aluminum, etc. Notice, and maybe make a note in your notes, that metals are conductors. Metals very readily allow charges to spread between them and move freely. And that's why we use metals when we build electric wires. Oh, last thing, looking at our two pictures, in our conductor, you can see that the positive charges are all spread out nice and evenly. In our non-conductor, they're all kind of clustered together because they just don't have the ability to move around. So, talking about electrostatic force. Now that we understand what charges are, we can actually talk about the force that these charges carry. The electrostatic force is how strong the attraction between opposite charges is. We can also use it to measure how strongly like charges repel. Okay? This relates to Newton's third law. Take a second, pause the video, and think, what is Newton's third law? All right, Newton's third law. For every action, there is an equal and opposite reaction, right? So, Coulombs law. This is measuring electrostatic force. We call it F, and we use that tiny little subscript E for electrostatic. Like every other force, we measure electrostatic force in newtons. Please take a second and write down this equation, all right? Fe equals K, Q1 times Q2, all divided by D squared. K is a constant, all right? We call it Coulombs constant. It is equal to 8.99 times 10 to the 9th Newton meter squared over Coulomb squared. Write down the units for that. All right, Q1 and Q2 are just the two different particles we're talking about, and we're giving the charges in coulombs. Last but not least, D is the distance between these particles, and we actually measure that distance in meters for this formula, okay? So sometimes, especially if we're talking about at an atomic level, this distance might be really, really, really small, and that's okay. Don't let that freak you out, all right? So take a second, make sure you got that written down before we move on. So this force, I want to take a second, our measuring of electrostatic force. We've got distance squared down here. So this is an inverse square law. And that means as our distance increases, the force we have goes down inversely, all right? We're increasing distance, but our force is gonna go down. And just like if we decrease our distance, our force is gonna dramatically skyrocket. So our first example, two spheres are given equal but opposite charge of 1 microcoulomb. That's not what I wanted to do. Okay, so let's get into our first example. Two spheres are given equal but opposite charges of 1 microcoulomb each. We want to calculate the force between the charges when they are separated by 0.1 meters. So here we go. So we have two charges, and I'm going to call them charge 1 and charge 2, and we're using Q for charge. Q1, Q2. We've got 1 microcoulomb, mu c. All right, and they are separated by a distance of, what did I say it was? 0.1? 0.1 meters, yep. Okay, and we want to know Fe. Okay, so the first thing we need to do is we need to take our charges. We can't use microcoulombs. We need to actually put it in terms of coulombs. If you look back at that slide, I said 1 microcoulomb equals 1 times 10 to the negative 6 coulombs. This negative 6 tells me that we can just put a decimal at the end of our 1 microcoulomb. Actually, over a little bit. 1 microcoulomb, and we're going to move it 6 spaces to the left. So here we go. 1, 2, 3, 4, 5, 6, and we're going to fill in zeros. So instead of leaving this as microcoulombs, I'm actually going to write 0.00001 coulombs. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Man, I cannot count, you guys. Struggle is real. Okay. All right. So now we need to find our force. We know that Fe equals K Q1 Q2 over D squared. Just so you know, D is perfectly fine. D for distance. Sometimes you might see R. It still means the distance in between these two charges, okay? If I ever say R, no, I'm really still talking about those distances between the charges. All right, so we know that K is a constant. Let's see, I'm just write it here. K equals 8.99 times 10 to the 9th. We're just gonna plug everything in. So I've got Fe equals 8.99 times 10 to the 9th. I've got my 0.00001 times 0.00001. 000. I'm missing a 0 every single time, you guys. I wish you were here to correct me. This is killing me. 0.000001 times 0.000001. And we're dividing that by 0.1 squared. All right. I will insert a screenshot of me typing this into my phone calculator so we can work through it and solve it. Okay. Okay, so I just took a second and I wrote down the problem on a scratch sheet of paper. And now we can get out our handy dandy calculators. So I know this isn't the easiest to see, but here's the formula that we need to be, not the formula, the numbers we need to be typing in. So we can start making sure our calculator is nice and cleared. 8.99. To do this times 10 to the 9th, we can use that second E function. So what you'll do is you'll type second, this blue button right here, and then you're gonna type, there it is, the comma, EE, and you'll get this E up here. The E is just the number in the exponent, okay? Just this 9. So I'm gonna type 9. Okay. times, let's do my set of parentheses, 0.000001, there's charge 1, times 0.000001, cool, divided by 0.1 squared. Hit enter. I'm getting that my force, F sub E, is 8.99. 8.99 what? What are those units? Think about it. Newtons. So I can write down here, F sub E equals 0.899, big difference, 0.899 newtons. Okay, though, something important to think about. In the problem specifically, the problem said that our charges were opposite. So if the charges are opposite, are they going to be attracted to each other or are they going to repel each other? They're going to attract each other, right? Opposites attract. That's going to tell us whether this force right here is a positive force or a negative force. If our forces are attracted to each other, we get a positive electrostatic force, okay? So this answer right here, 0.899, is a positive value, and we make sure we include our sign and our units. Put a nice little box around it, and we're ready to move on. All right, so our second example actually relates directly to the first. We're asking what's gonna happen to our force if we quadruple the distance between them. So I want you to take a second and try this problem on your own. The only thing we are changing from example 1 to example 2 is our distance. When we quadruple, we're really saying that we take our distance and multiply it by 4. Take a second, try the problem, pause the video, and when you're ready, resume it, and I'll show you my problem all worked out, okay? All right, sorry about that. So here we go. Q1, just like in the first problem, is 0.000001 coulombs. Charge 2 is 0.000001 coulombs. K is a constant. It is always going to equal 8.99 times 10 to the 9th Newton meters squared over coulombs squared. The only thing that's changing is our distance. So we've got our distance equals, it was 0.1 in the first problem, but we're quadrupling it, so we're going to multiply that by 4, which gives us 0.1 times 4 is 0.4 meters. All right, now let's plug all that into our formula. Fe equals K, Q1, Q2 over D squared. Sorry about that. Make sure that's focused. All right, so my electrostatic force, F sub E, equals 8.99 times 10 to the 9th, parentheses, because I love my parentheses, 0.000001 times 0.000001 divided by 0.4 squared. Take a second and plug all that into your phone calculator. Here we go. I'm just gonna go second, that blue button, and then enter says entry. So I'm gonna just pull up that last entry, and instead of 0.1, I'm gonna delete that and say it's 0.4 squared. All right, and our answer, F sub E, my electrostatic force, is equal to 0.056, we'll do 3 sig figs, 0.562 newtons. Once again, think about it. Are our charges the same sign or are they opposite signs? If they are opposite signs, opposites attract and we get a positive force. Put a box around it. Okay. Okay, going back to our PowerPoint, 0.0562 newtons is the same force that we got. For reference, that is 1/16 the electrostatic force from problem 1. Why do you think it's 16? Why is it 1/16? Jot that down. That might be a question on your exit ticket. Okay. So for reference, I want you to compare that, both of those forces in problem 1 and problem 2, with the force of weight for an average 70 kilogram person. Now remember, weight is the force of gravity on a person. So we're doing Fg for a 70 kilogram person, all right? Include that in your notes, jot it down. I'm gonna ask about it in our Zoom session. So that's it for today's lesson. I've got our exit ticket right here. This is going to be the problem that I am going to assess on our Google Classroom, all right? If you look in Google Classroom, you'll see that there are a bunch of problems posted that I want you to try. If you have any questions, mark them up and we could talk about it in our Zoom session tomorrow, all right? I look forward to seeing you all very much. I miss you all tons, and I'll talk to you later. Love you. Bye.